Okay, hello everyone. My name is Youngju Chung at the GIST. GIST is a Gwangju Institute of Science and Technology, and it is in Korea. And it is a great pleasure for me to give a presentation at Wolfram Technology Conference this year. The title of the talk that I'm going to give today is Tensor Analysis and Applications. This is the abstract. Tensors are used in various areas of mathematics and physics, particularly in theoretical calculations involving fields in vector spaces. Well, I'm going to skip the rest of it. And I'm going to use a package called Mathsymbolica for tensor analysis. And this is an add-on package for symbolic computation in Mathematica. So I'm going to give a brief introduction to the package, and then I'm going to give some examples in differential geometry and electrodynamics and the general relativity. Okay, so I need to load the package. It is done by this, and I have already done it. Well, I'm going to give a brief introduction to this package. So this is an add-on package for Mathematica, and it has over 1,000 functions. This is a pretty big package, and I can do a display and interpretation of various mathematical expressions like derivatives and integrals and sums, etc., using the traditional notation. So this is a notation is built in the package. This was written by me, and the homepage is given here. So the keywords is the notation, as I mentioned, and I can manipulate and evaluate various mathematical expressions using the functions in the package. So the motivation is to design and implement a symbolic computing system based on Mathematica that can manipulate the various mathematical expressions using the traditional notation. So it gives the capability to use the notation that is typically used in mathematics and physics. And also it has a deferred on-demand evaluation, which means that I can write sums or integrals, etc., but they are not evaluated. Well, in Mathematica, it is evaluated immediately, but once the package is loaded, those are not evaluated. So I can do transformation and etc. I can do a manipulation of those expressions. And then I can evaluate the expressions when I need it. So this is a deferred on-demand evaluation. And the objective is to replace handwritten calculation with a symbolic computation and the software-based automation. And then these are the features and advantages of using the package. So it integrates seamlessly with the computing environment of Mathematica, and it gives a powerful platform for streamlined manipulation of mathematical expressions. So one function, which is called SCMAF, which means SC map apply functions, and all functions in the package start with SC, symbolic computing. And using this this function, I can apply a sequence of functions like F1, F2, F3, etc. And these are the functions. Let me make it a little bit larger. So these are the functions, and these are the arguments, and these are the local options that is applied to these functions. Then I can apply a sequence of functions inside this SCMAF. And then the starting expression, it is processed through these functions. and then I can obtain the final form that I want. So these are the advantages of using this package. And so by using this package, we can focus on the concept and the principles rather than the tedious, boring, and the time-consuming and error-prone handwritten calculation. And it gives a good readability because I can use the traditional notation as I do with my handwritten calculations. And it gives enhanced speed and accuracy, and the human errors are minimized during the calculations. Well, it has a pretty long history. I started the development of the package about almost 20 years ago. And then I presented this package in various Korean domestic conference, like a Korean Mathematica Users Conference, starting from 2007. And also I gave the presentation at Wolfram Technology Conference in 2011. And then the versions now, the latest release is 6.0.2. And I was awarded Wolfram Innovator Award in 2017. And then there are two packages. This is the symbolic computing package. And using this, palette. Using this palette, I can enter various expressions. Various expressions like, as you can see here, well, here and here, let me show you. So this is the package, the palette that I'm using. And then I can enter the vector operators and the derivatives, integrals, and the sums, etc. using this palette. And these expressions are the traditional mathematical expressions. And I can use these in the mathematical notebook. And this gives a very, make it easy, very easy to enter the expressions. And also the results are also given in these traditional notations. Okay. And the number of, the package has been continuously updated. And recently, the total number of functions in the package is now, has exceeded 1,000. Okay, let me go to the, well, let me show you some of the references that I used for my presentation. For mathematical methods for physicists, and some of the okay, let me well, so these are the notations and the partial derivatives. So these can be these are the partial derivatives, and also we use the comma. A comma for the partial derivatives and the partial d, and these are the notations for the covariant derivatives, the semicolon using this. So you can see that this is a Mathematica input, and okay, and this is the covariant derivative of second order the tensor, and also there is a notation using this nabla. So, so these two, the semicolon and the nabla, these are the notations that are typically used in the literature. And they can be also converted from one form to the other. So from partial comma, this is a SC function. And this is the comma notation, and then it is converted to this fraction. And also it can be converted back to the comma notation. And also here from this to this del. Okay, and then it can be also converted. And also this is the expansion between different notations. As is from cobalt derivative, and this is from cobalt D, and this is expanded to this form. Okay, this is Einstein summation convention. It is the summation convention for the dummy indices. So for example, A, I, where I appears twice, it is a summation. And A, I, B, I is also the summation of I. And I, J, X, J, J is the dummy index. So this is equal to this. So using this convention, A, I, and A, J, J are actually equal. So using this function, SC tensor contract, you can see that this is equal to 0. And likewise, AI, BI, and AI, J, BJ are also equal. So indices can be raised or lowered by contracting with the metric Gij or G superscript Ij. So AI is Gij, Aj, and you can show that using this function, SC separate the metric. Let me show you. This is the help. The self-metric, you can see that this is converted to this form. So x mu superscript is changed to x subscript lambda, and it is multiplied. G, the metric is multiplied. So indices can be okay, and then here A super I is Gij, Aj. So this can be converted using this function. Right. Let me show you. So metric tensor. So in Cartesian coordinates, the distance ds is given by this. ds squared is a dxi, dxi. So this is a summation over I, and x1 is x, x2, y, etc. And then using this function, SC trans tensor, dxi is written like this. So this is conversion from to x prime. So in terms of x prime I, the distance ds is here. Let me show you a step by step. Okay, so dxi. So this center dot is to separate the two. And then this is it. So dx here, this is a dxi, and this is a dxi. And here, I'm using these two different dummy indices, j and k. Okay, and then this can be removed like this. And then this is the definition of the metric gjk. Okay, like this. So gjk is given by this expression. So dropping the prime, the general relation can be put in this form, and the metric tensor Gij for 3D is given by this, by summing over this x coordinate. So for example, for the spherical coordinate system, x sup 1 is r, etc., and x, y, g in Cartesian coordinates are given by these expressions. And then on the right side, by expanding in the coordinates, now this is okay. So x1 is r, x2 is etc. And so putting all these in here, and then by evaluating the derivatives, you obtain the elements of the metric Gij. So these are the elements of the metric tensor for the spherical coordinates. So geodesic, this is the curve for the shortest distance. So in the length element, the Cartesian coordinates are given by this. So these are the length element in Cartesian coordinates. Now, suppose we have a three-dimensional surface that is expressed as this. Then you can see that, well, I have expanded this step by step, and I'm using the functions like derivative expand and the compact derivative and essentially EQ map. So these are the functions that are applied in sequence to the input expression here. So here the fxy, let me show you by step. So g is changed to f, and then it is expanded. Okay, so this is the final form, and so for the geodesic, the Euler-Lagrange equation is, if I put this in here, then and evaluating all these derivatives, we obtain this equation. But if f does not explicitly depend on y, then we can drop this term. Okay, this term. Then this is a constant. That is the solution. And then putting f in here, you can see that. So if I put f in here, then okay, then because f is a function of x only, then we get this. If you evaluate the left side, then we get this. So this is, for example, for a cylinder of radius r, g is given by this. Okay. Oops, sorry. Like this. So we can write, put f in here, then we obtain these two equations. So the solution is given by this, and then using this solve, we obtain the solution. So introducing a parameter theta and putting x equals r sine theta, we get these results. Okay, well, for the electrodynamics, the field strength tensor, the vector E is given by this, and then exponents of E and B are explicitly given by these results. So the field strength tensor is in matrix form. You can see that putting EX and EY, EG, you can see that F alpha beta is given by these elements. Then the covariant form of the field strength tensor is F alpha beta is given by this. Then this is the product of the three matrices. This is a G alpha beta, alpha gamma, F alpha gamma delta, and this is G delta beta. So multiplying these, then we obtain these expressions. And similarly, we can obtain the dual field strength tensor, F Colli F alpha beta, and then we can obtain these expressions. Okay, well, let me skip this. It's a similar. Okay, we put this in here, then you obtain these are the Maxwell equations, and then we obtain these forms. So they are it can be written in this form. Okay, the last topic is the general relativity. Well, and here this is B mu, and this is the covariant derivative. This is a tensor. And then we can show that these are the functions that are applied: trans tensor and the tensor RA, transderiv, etc. So I apply these functions in sequence, and then you can see that it is evaluated like this. then these are automatically generated. These are the automatically generated indices. And then it can be written like this. So this is the transformation rule for the new row covariant derivative, and this shows that it is indeed a tensor. So this can be directly written using the tensor in this form. And similarly, we can prove that covariant derivative. This is very complicated. It's very complicated, but and eventually I get these results, and it is equal to this. Okay, because this term is equal to this. So this shows that this is also a tensor of rank 4. And then this function directly gives this result. Okay, and the fully covariant form of the curvature tensor, it is contract metric, or it is equal to this, and therefore this equation, this is the raising of the index, and this is the metric tensor, and then it is. You can see that if I put this in here, then I get these results. Well, I'm going to skip the details, and then we can obtain the expression for this Riemann tensor. And we can also show that it is the symmetric, for example. Okay, and on the right side, if we expand it, then most of the terms cancel. They cancel, and it becomes this result. And you can see that this is nu kappa lambda mu. Lambda mu nu kappa is R nu kappa lambda mu. So this is the symmetry. And it is also has antisymmetry. If I exchange like lambda and mu, then it changes sign. So here on the right side, if I expand it, then most of the terms cancel. And also, so the Ricci tensor is given by this. All right, finally, this is a paper. These are the authors, and this paper was published last year. And then I used the package functions to prove some of the relations that are derived in the paper. So this is a calculation of the connection coefficients, and then you can see that it is very complicated, but it is. You can let me show you. So it is what these are evaluated step by step, and then finally I get this result. So this is the final form. Okay, the rest of it is very similar. You can obtain the components of the Ricci tensor, which are given by this. And then by putting in the results that were derived earlier, then you can show that these are the R00, and this is R0I, and these are Rij. So you can see that the result is very, very complicated, but we can derive these results using the package functions. And the Ricci scalar, it is if I put in all these results that were derived earlier, then finally it is, okay, this is the final result. And I have checked that all the results that are derived here are the same as the results that these authors, they did it by hand, and they are identical. Okay, oops, sorry. I don't know what this is. Thank you for the attention, and this is all I have today. So let me check if you have any questions, then I can answer the questions. Oops. Sorry. Let me see. Well, there are some questions. I handle differential, yes, differential forms, yes. Operation like tensor widgets and the products. Well, differential forms. Let's see. Here, let's see. Let's see. Expand. Okay. So derivative expand. This is the package function, and then so these are the differentials. These are differentials, and and the tensor wedges and the products. Well, it can the transformation rule is given, then it can be applied using the RA or the replace or tensor RA, which is the operations for the tensors between the weak and the strong summation conventions. Well, the weak summation convention, strong. Well, I'm not familiar with this notation, but basically the tensor contract. Let's see tensor contract. Here it is well, sims, these are the names of the symmetric tensors, and the asims, these are names of asymmetric tensors. And also here the symmetry, it is symmetric and antisymmetric, and the Riemann or Bayer. So for example here, this tensor contract, and then the symmetry R Riemann means that R is the Riemann tensor. And here symmetry C is a Bayer. And then by applying the symmetry and antisymmetry properties of the Bayer tensor, you can show that this is indeed equal to 0. And similarly, this is a covariant derivative, and this is equal to 0. So for other expressions, it is basically the summation convention. It is simply if the indices appear twice, then it it is considered as the summation. But I'm not familiar with this weak and the strong, and I'll take a look into that. Oh, I see. And the other is the covariant. Yeah, of course it is. Let me see here. It is. You can. And here, tensor contract. Here you can see that it is. This is the superscript, the superscript and the subscript. And also you can you can use if the two indices are in the subscript, as I showed, it is also considered as a summation. So it can distinguish between the two, like this. Here it is II. Yeah, both of the it is in the subscript, and it is considered the summation. And also, if it is one is like this, here J and J superscript and the subscript, and it is also considered the summation. How do I get this? Now I opened. So this is the homepage I opened recently. When it is not yet finished, it's not yet. So it is here. Symbolica is a commercial software, and if you contact here, then you will get how to get it and the information on the pricing, etc. Okay, so perhaps I should close. Okay, all right. Let me stop here today, and thank you very much for coming to my talk. I hope you enjoy the rest of the conference. Thank you.